Plenty of room here. Let's get started. In case you were a little confused, I'm not Chris Van der Valle and Keisha is not Leon Lorenz. We were listed as Colin's advisors in the announcement. Yes. Yeah, you can tell that we're not reading the break. So, time has come for Colin to present to us what he's done for his PhD as an entire package. It's been a difficult problem. This. And it has been a tough problem. I think when Colin first showed me the very first experiments, I said, "This is horrible. What are we going to do with this?" But he's made sense of it, and he's done a really thorough job in terms of doing an experimental exploration of compositional effects on oxidation, and then linking it to phase equilibrium, etc. So we'll see now what the whole story looks like. Colin, please get started. Oh, and we welcome Colin's family, who's here.
Yes. Yes, thank you. So today we'll be discussing my dissertation research on the accelerated design and characterization of oxidation-resistant cobalt-based gamma-gamma prime superalloys. And this work is the product of many people beyond myself. So I'd like to start by thanking our industry collaborators at GE Global Research, Akane Suzuki, Dalmeth-Kin, and Scott Weaver, my committee, of course, and our funding source, the NSF DEMRA program. So today we'll be discussing materials that are used in turbine engines. And turbine engines power huge industries of both aviation and electricity generation, where we burn natural gas in large industrial turbine engines. And we can increase the efficiency of these engines by increasing the temperature at which they burn at, with every 30 degrees C increase leading to about a 1% increase in turbine efficiency. And while 1% might not seem like a lot, because these engines are used so extensively, we're really talking about hundreds of billions of dollars. But in order to burn at these higher temperatures, we of course need materials with higher temperature capability. Now, in the hot section of turbine engines, right now, the material that we use the most is nickel-based superalloys. And this material needs to have a variety of high temperature properties. It needs to have some measure of high temperature mechanical stability, primarily creep resistance, because these are structural components. But they also have to have some measure of intrinsic oxidation resistance. While many of the sections in the hot part of the turbine are coated with protective barrier coatings, there are a variety of mechanisms through which these protective coatings can fall off, and not all of the components in the hot section are coated. So we'll need to have our structural superalloy with some measure of intrinsic oxidation resistance. And I will say that some of the temperatures that these blades in the hot section of an aero engine can see are in the range of 1,000 to 1,200 degrees C. So as I mentioned, many of the components in the hot section of turbine engines are made out of nickel-based superalloys like CMSX4. However, the nickel-based system is considered to be reaching maturity as the gamma prime solvus temperature, where our strengthening gamma prime precipitates dissolve back into solution, approaches that of the solidus temperature, where our material begins to melt. So we don't have a lot of room to continue boosting the temperature capabilities of these alloys. But fortunately, in 2006, Sato et al. Discovered that the cobalt tungsten aluminum ternary system has this two-phase gamma-gamma prime field that also has the same characteristic cuboidal microstructure as our nickel-based alloys. But in the cobalt-based system, we have a solidus that is over 100 degrees C higher. So this gives us room to potentially increase the temperature capability beyond that of nickel. But what you'll notice is that in the cobalt ternary system alone, while the solidus temperature is higher, the gamma prime solvus temperature is quite low. So we'll need to begin boosting up that solvus temperature via, for example, alloying additions. We know that tantalum and nickel additions both boost up that gamma prime solvus, but elements that we might add for other reasons, like oxidation resistance via chromium additions, can depress the gamma prime solvus. So we'll need to think about both of these properties together. So today we'll be asking the question of how can we achieve a cobalt-based alloy that has both a high gamma prime stability and some measure of oxidation resistance. How does changing our alloy chemistry affect our ability to achieve both of these properties? Now, to address this question, we'll be applying high throughput experimental techniques in combination with modern computational tools to achieve an accelerated alloy design procedure and a more rapid fundamental understanding of this material system faster than the multiple decades that nickel-based superalloys have been under development. So I'm going to start by talking about some relevant oxidation phenomena that we'll be using going forwards. So thermodynamics tells us that the oxidation reaction in these alloys is really going to be unavoidable. For oxidation to proceed, the change in Gibbs free energy for that reaction must be negative. And we see that for many of the elements found in superalloys like cobalt, chromium, and aluminum, the change in Gibbs free energy is negative under our temperatures of interest. Of course, we are not discussing pure elements, but rather alloys. So we'll also need to take into account the changing activities and chemical potentials of our different constituents. Now, this is important because if our Gibbs free energy becomes positive, this oxidation reaction will run in reverse, where our oxide dissociates back into its metal and oxygen components. And what we can do is use this Ellingham diagram to get a sense of what the different layers of our oxide might look like in a multi-phase oxide scale. So, for example, in an alloy that can form both chromia and alumina, what you might expect is moving from our oxidizing environment down into our alloy, we are lowering the partial pressure of oxygen. So as we lower partial pressure of oxygen, we'll get to a point where chromia becomes unstable. But because of its high oxygen affinity, alumina is still stable. So we would anticipate a chromia scale to form above our alumina scale. And then continuing to move down, we'll continue to lower the partial pressure of oxygen until we get to our alloy. So thermodynamics is telling us that these oxide phases will form, but the other half of the equation is kinetics. And kinetics tells us that despite them forming, we can slow this reaction down. Once an oxide scale is established across the surface of our material, the continued growth of that oxide layer will be mediated primarily by either the inward diffusion of oxygen anions or the outward diffusion of metal cations. And if this process is diffusion limited, then we can describe it with a parabolic rate using Fick's laws. So basically what we'd like to do is to engineer our alloys such that they form an oxide across the surface that has a very low growth rate. And alpha alumina is a nice candidate because it has a low defect concentration, so it will grow very slowly. So this will be our goal today, is to form a slowly growing alpha alumina scale. Of course, there's an added complication in that alumina can form not just as a continuous scale across the surface of our material that protects against the rapid influx of oxygen, but instead it can form as these discrete internal particles inside of a metal matrix that allow the continued diffusion of oxygen to keep attacking our metal component with these thick undesirable oxides resulting. So we really like to engineer our alloy composition to achieve this continuous and more protective alumina morphology. Now, if we're kind of in the boundary between these two behaviors, what we might expect is for our alloy to initially form these discrete alumina particles internally, but in some locations form continuous patches of alumina that locally block the inward flux of oxygen. And these patches can then grow laterally and undercut our internal oxidation regions. And we're left with a continuous scale, but we have these thick portions of undesirable oxides on the surface that have eaten up some of our metal components. So again, our goal will be to form not these discrete internal alumina particles, but rather a continuous alumina scale, perhaps with a small amount of other oxides on the surface. And we'll be looking at conditions of about 1100 degrees C, and to start with, just 1 hour in air. Now, for reference, the second generation nickel-based superalloys are considered to have very desirable oxidation behaviors. We see that CMSX4 and Rhenean5 are both able to form this continuous alumina scale. And we get in CMSX4 a small layer of other oxides, about 2.5 microns, including some spinels on top. Now, in comparison, when we look at cobalt-based alloys under the same conditions, we see that it's very difficult to achieve a continuous alumina scale. This is some recent work by Ye et al. And in this alloy, we have a large internal oxidation region of those alumina particles and a thick amount of undesirable oxides on top. Now, this research group was able to engineer their alloy to form a continuous alumina scale. But in doing so, they've lowered the tungsten content and depressed the gamma prime solvus by over 100 degrees C. And I think that this really highlights our challenge in this material system of achieving both properties together, a high gamma prime solvus to give us that high temperature mechanical properties, and some measure of oxidation resistance by the formation of a continuous alumina state. So again, to address this question, we'll be employing a series of high throughput experimental techniques. And the first one that I'll talk about is a combinatorial synthesis technique, where we've created a large amount of samples all at the same time using a synthesis technique called ion plasma deposition, or IPD. In IPD, we arrange 3 different alloy cathodes of 3 different compositions over an array of substrate buttons. We can then charge these cathodes under vacuum to deposit the material simultaneously as a plasma. And this creates a gradient in composition across the buttons depending on how close you are relative to each of the cathodes. So the benefits of this technique are that they create a large amount of samples with a variety of compositions all at the same time. And we're also creating relatively thick coatings of about 100 microns. Now I'll point out that in order to explore space relevant to cobalt-based gamma-gamma prime alloys, we've created all of these samples that have all 6 of the elements shown here. We've got cobalt, tungsten, and aluminum to form the basis of the gamma-gamma prime structure. We've got nickel, which has been shown to expand that gamma-gamma prime 2-phase field of interest. We have chromium, which is known to promote alpha alumina formation. And we've got tantalum to boost up the gamma prime solvus. So we've created 3 separate libraries, all of them increasing the nickel to cobalt ratio moving to the right. And by exchanging this 3rd cathode on top, we can look at the effects of changing aluminum content, changing tungsten content, and changing chromium content. Now I'd like to mention that these alloys that we're creating with the combinatorial synthesis are meant to represent the structural superalloy compositions themselves, not the bond coating compositions. So as we observe in cross-section, we'll have after deposition this combinatorial alloy that we'd like to investigate. And just after the IPD technique, it's somewhat heterogeneous. So what we'll do is apply a homogenizing solution heat treatment and then polish the surface to about a 0.05 micron finish. And this leaves us with a smooth surface, a coating of about 100 microns with 7 micron grains, such that when we do our oxidation experiments, the oxidation reaction will be contained inside of this alloy of interest. Okay, so let's take a look at our first combinatorial library. Here I show the concentrations of different elements as measured by SEM-EDS prior to oxidation. So we've got higher concentrations in red and lower concentrations in purple. And you can see that as we move up across our library, we're going towards higher aluminum content, whereas moving to the right, we have higher nickel to cobalt ratios, with the other elements fairly constant, and those in white I haven't gotten to. So we'll then take these alloys and we'll oxidize them under our target conditions. And what we have is a furnace that's been preheated to our conditions of interest, 1100. And this is contained inside of a sealed quartz tube. So this is filtered air flowing at a slow laminar rate. And after we've heated it to our target conditions, we'll inject our samples into the hot zone for the prescribed amount of time, and then withdraw them so that we can analyze the oxides that have been formed. So to quickly analyze all of these different samples that we've created, we've employed a non-destructive technique called photostimulated luminescence spectroscopy, or PSLS. In PSLS, we shine a laser at the surface of our sample and look for the presence of a characteristic alpha alumina doublet at about 14400 wave number. We can then take a series of measurements across the oxidized surface of our button and look for how many of those measurements exhibit the characteristic alpha alumina doublet. So for example, in this button 36A, we found that 79% of the measurements exhibit the characteristic alpha alumina doublet, so we'll color it green, whereas this button 35A has none of the measurements exhibiting alpha alumina, so we'll color it red. And in this manner, we can observe transitions as we move across our combinatorial library towards more strongly alumina forming regions at higher aluminum contents and greater nickel cobalt ratios. So this kind of lays the groundwork for how we'll proceed through all of these different alloys moving forwards. But first, I'd like to take a little bit of time to dig into our PSLS technique and examine what it's actually measuring and how it works. To use this non-destructive laser technique as a screening method, we'd like for it to answer the following questions. Can it identify samples that have a continuous alpha alumina scale? And can it also identify samples that have lesser amounts of undesirable oxides on top, which will tell us that there's less amounts of metal being eaten up by that oxidation reaction? So to see if our non-destructive technique is giving us this information, what we'll do is compare the non-destructive PSLS measurements to the actual oxide morphologies we observed by cutting the samples open and looking at the cross sections. So here we'll start with this button 31B, where we're not observing alpha alumina with our PSLS technique. And indeed, we can see that in cross section, our alumina is forming these non-protective internal oxidation zones of discrete alumina particles inside of our metal matrix. And because this is a non-protective morphology, it gives rise to these large amounts of undesirable oxides on top. So we've got an outer layer of nickel cobalt monoxide. Then we've got a layer of mixed oxides, including spinels. A second layer of mixed oxides, including tungstates, shown in white. And then our IOZ, and further down we have our metal that's not yet oxidized. Then as we move across our library towards samples where we start detecting alpha alumina more and more frequently by PSLS, we see indeed the rapid onset of this continuous alumina scale shown in black. And as we detect alumina more frequently from the surface by PSLS, it looks like our oxide scale gets thinner and thinner. So we will continue to cross-section some of these buttons and compare the non-destructive PSLS results with the scale thicknesses that we measure experimentally in cross-section. And by plotting these two different techniques, we observe that there's a nice trend, and that by selecting those samples where we have more frequently detected alpha alumina by PSLS, we can also select those samples with a lesser amount of oxide scale without having to go through the trouble of cutting them open. So this will be a nice rapid screening technique as we move through and explore all of these different alloys. But we'd also like to ask the question from a scientific perspective of why is it that PSLS is giving us a sense of how thick this overlying scale is? Perhaps some of the overlying oxides are attenuating the PSLS signal. So what we'll do is we'll start by investigating this outer cobalt nickel monoxide layer because it will block both the incoming excitation beam as well as any outgoing excited signals. And to investigate this, what we've done is create a series of model samples where we've deposited a layer of either cobalt monoxide or nickel monoxide on top of an alpha alumina substrate with a small layer of spinel reaction between them. We can then polish these model samples on a tilt and take PSLS measurements across the small angle tilt to look at what are the effects of changing oxide thickness on our ability to detect that underlying alpha alumina. So here we show some optical micrographs of two different model systems. We have a nickel-based system on top and a cobalt-based system on the bottom. And we have our tilt horizontally, such that on the left, we have our exposed alpha alumina substrate. We then have a thin layer of that spinel. And then on top, we have our monoxides getting thicker and thicker, moving to the right. So we can take some PSLS measurements, and what we observe in this nickel-based sample is that we are detecting an alpha alumina doublet on the exposed alpha alumina substrate. And then as we move and start looking through larger amounts of nickel-based oxides, the intensity of our alpha alumina doublet decreases, and we start seeing the presence of these nickel monoxide larger peaks. But you'll notice that even through about 22 microns of this overlying nickel oxide, we can still faintly detect our alpha alumina substrate. And this is in contrast to the cobalt-based system, which has a very different behavior. In this cobalt-based model system, we see that we are detecting alpha alumina on the exposed substrate. But then as we move through our spinels and reach our cobalt monoxide, we see a drastic reduction in the alpha alumina doublet intensity until we can no longer observe alpha alumina through about 4 microns of cobalt oxide. So this is telling us that not only is our PSLS signal dependent on the oxide thickness, but also the composition, with those overlying cobalt oxides being more opaque. But overall, we've observed that we can use this PSLS technique as a screening method to rapidly look through our samples and identify which are forming that continuous alpha alumina layer and thinner amounts of overlying oxide. So next, let's apply this to all of our different combinatorial results. What I'll be showing you is a series of phase diagrams that are isoconcentrate sections. which means that inside of this Gibbs triangle, we'll be varying the 3 different elements depending on how close you are to the corners. But everywhere inside of this Gibbs triangle is at a constant composition that I'll show, which means that at the corner, we don't have 100% aluminum, but rather, for example, 85.6% aluminum with the other constant elements shown here. And inside of this Gibbs triangle, we'll be plotting different alloy phase fields as calculated by the thermodynamic database PANDAT. This is courtesy of Junzhu Computer. So while this is a calculated phase diagram and should be taken with a grain of salt, it does give us a general sense of what alloy phases that we might expect. So here we have our solid solution matrix gamma phase. And then as we move up in aluminum content, we have our gamma-gamma prime 2-phase field of interest. And while both the gamma and gamma prime phases exist across a large portion of our library, we might also anticipate the precipitation of other alloy phases, like the tungsten-rich mu phase or the aluminum-rich beta phase. Okay, so on top of this phase diagram, I will be plotting our combinatorial buttons that we've experimentally measured, and we color them based on those PSLS results. So we move towards more strongly alumina-forming behavior as we go towards green. And what we observe is that it appears we have a region of more promising oxidation behavior above about 11.2% aluminum and 22% nickel. So this gives us a sense of, if we'd like to engineer an alloy with more promising oxidation resistance, this might be a good region to start looking. We'd also like to ask the question, which of these elements, aluminum versus nickel, is having a stronger effect on our oxidation behavior? So to assess that, we can take some cross sections of the buttons and move along isoconcentrate lines to look at the changing morphology. So here we've moved horizontally in the plus nickel direction, and we observe that we have a continuous luminous scale here at the bottom, but there are some of those undesirable oxides on top. And as we increase the nickel content, we are shrinking the undesirable scales, but a lot of those phases are still there. And this is in contrast to the behavior when we look along the plus aluminum direction, where we're getting a nice reduction in scale thickness above the continuous alumina layer. And many of those undesirable phases are prevented, where we're getting rid of a lot of those tungstates and a lot of the overlying monoxide. So this is telling us that aluminum is having a stronger effect on our oxidation behavior. We've outlined this region of more promising oxidation resistance. And we've also seen one of the thinnest scales so far of about 6 microns, including this continuous alumina layer, which is desirable. Okay, so next, let's take a look at our second combinatorial library. In this library, we'll be investigating lowering the tungsten content as we move up, and again, increasing the nickel to cobalt ratio as we move to the right, with the other compositions held fairly constant. We can, again, oxidize these buttons under our target conditions and apply our non-destructive PSLS technique to rapidly look for regions of more promising oxidation behavior. Now, this time I'm showing you a phase diagram that's a new slice through composition space. We have increasing nickel across the X, but now we have increasing tungsten across the Y. So as we slice through composition space now, we have a larger section of the gamma-gamma prime 2-phase field. We have, again, some of those alloy phases we might expect to precipitate, including the tungsten-rich mu phase and aluminum-rich beta phase. And PANDAT is suggesting that as we increase tungsten too much, we might expect the precipitation of a BCC tungsten phase. So we will again plot our combinatorial results, and we observe this nice trend in oxidation behavior, where as we increase our tungsten content, we observe that there is a region of more promising oxidation behavior between about 7 and 10.2 atomic percent tungsten, and again at higher nickel contents over about 22% nickel. Now, again, we can cross-section some of these buttons just to confirm that we're getting these effects and what the effect of adding tungsten is on our oxide scale. And you can see that it is decreasing a lot of those undesirable oxides. In this sample down here, we have a continuous alumina scale, but we can't detect it by PSLS because of all of these thick overlying oxides. And while adding tungsten does decrease the thickness of that scale, we still have a lot of those undesirable oxides on top. Now, this is an interesting result because in our last combinatorial library, it made sense that increasing the aluminum content would increase our ability to form aluminum oxide. But why is it that changing the tungsten content is having an effect on our ability to form alumina? Well, one thing that we might want to dig into is how tungsten is changing our thermodynamic driving forces. So here we show some first principles density functional theory calculations, courtesy of my group mate, Rob Ryan. And these are calculated at 900 degrees C for the ternary cobalt aluminum tungsten system, as well as the nickel ternary system. And what we observe is that in the cobalt-based ternary system, as we increase our tungsten content, we're lowering the chemical potential of aluminum, which lowers our driving force to form alumina. But in the nickel-based ternary, we're observing the opposite behavior, where as we raise tungsten, we're raising the chemical potential of alumina. So perhaps in a quaternary system, increasing the tungsten might raise the aluminum chemical potential, the aluminum activity, and increase the driving force to form aluminum oxide. Now, of course, we'd like to actually do these quaternary calculations, and our experimental alloys are more complicated still. They are 6 elements. But I think this gives us an interesting perspective on what might be going on in the thermodynamics and warrants further computational experiments. So overall, from the second combinatorial library, we've outlined a region of more promising oxidation resistance at higher tungsten contents. We, based on our first principles calculations, suggest that this beneficial effect might be due to tungsten's effect on the aluminum activity. And because in this library we've lowered the tungsten content, and that did not help our oxidation resistance, the thinnest scale we've seen is still from that aluminum-rich library of about 6 microns. So lastly, let's take a look at our third combinatorial library. Here we are increasing the chromium content as we move up, and increasing the nickel-cobalt ratio as we move to the right. We will again oxidize these alloys and investigate them using our PSLS technique. And we observe that there is more promising oxidation behavior at higher chromium contents and greater nickel-cobalt ratios. So here we'll be plotting those results on a phase diagram with increasing nickel to the right and increasing chromium content as we move up. And we'll see that as we slice through this composition space, while we do have our gamma-gamma prime phase fields, we also have the precipitation of mu and beta phases, and perhaps at higher chromium contents, a BCC chromium phase as well. Plotting our combinatorial alloys, we observe that we have a more promising region of oxidation behavior above about 3.5% chromium and 25.5% nickel. Again, we'd like to ask which of these elements is having a stronger effect on our oxidation behavior. So we'll take some cross sections, and we observe again that by increasing the nickel content, we do decrease the scale thickness somewhat, but a lot of these undesirable phases are still there. And this is in contrast to changing the chromium content, where we greatly reduce our scale thickness. We've gotten rid of almost all of these tungstates and overlying monoxides, and we're left with the thin oxide layer that's continuous alumina with primarily an overlying spinel. And this is also promising because this is the thinnest scale that we've observed so far of about 2 microns. And that's actually comparable in scale thickness to the second generation nickel-based superalloys under the same conditions. So this is a really exciting result. But of course, you'll remember that the superalloys that we'd like to design have both some measure of oxidation resistance and a high gamma prime solvus for that high temperature mechanical properties. So this is just one part of the equation, and we need to continue refining this alloy system. So moving forwards, I'll be discussing the development of some novel alloy systems that we've made called the DEMRAF alloys. And these were designed using that foundation of knowledge that we've developed so far. So we found that aluminum and chromium additions both strongly benefit our oxidation behavior, that nickel and tungsten additions somewhat benefit our oxidation behavior. We've outlined this region of composition space that might be a good starting point for oxidation. And now to find alloys that also have a high gamma prime solvus in the gamma-gamma prime 2 phase field, we can combine this experimental data with our thermodynamic databases. So what we'll be doing is plotting these results on a phase diagram with increasing tungsten moving to the right and increasing aluminum content moving up. And based on our combinatorial results, we see that a good starting place might be about 25% nickel and 2% chromium. But when we calculate that phase diagram, we see that we're not predicted to cut through the gamma-gamma prime 2 phase field of interest. So what we'll do is we'll boost up the nickel content to stabilize the gamma prime phase. So now we're taking a slice through increased nickel content, And we see that we are cutting through the gamma-gamma prime 2 phase field. Plotting our combinatorial results to look at the oxidation behavior, we see that we can achieve compositions such as this button 26G, which have both a continuous luminance scale and fall within that gamma-gamma prime 2 phase field. And just to confirm this experimentally, we do see that we are having the gamma-gamma prime 2 phases experimentally after oxidation. And we do have a continuous layer of a luminance scale, although there is some room for improvement. Now, we'll use this as a starting point for designing our DEMREF alloys going forwards. But before we do, we'll like to verify this composition using EPMA. So next, what we'll be doing is outlining our design space by moving towards the edges of our gamma-gamma prime 2 phase field in directions that we know will benefit our oxidation resistance. So we know that increasing the aluminum content will be good for oxidation behavior. So we'll call this composition DEMREF 8. This is made by Sean Murray. Thank you very much. And we see that in addition to the gamma-gamma prime phases, we also have a small amount of the aluminum-rich beta phase, which means that we've slightly passed into this 3-phase gamma-gamma prime beta, but we are pretty close to the 2-phase field. And while it's hard to see the gamma prime phase, this has been verified experimentally by XRD. And our oxidation behavior, we're getting a continuous alumina scale with thinner amounts of undesirable oxide on top compared to our combinatorial alloy. Next, we'll investigate another corner close to the edge of the gamma-gamma prime phase field. And this time, we'll be increasing the chromium content, which we know will benefit our oxidation behavior. We'll be increasing the aluminum content, but now to stay inside of this 2-phase field, we'll be lowering the tungsten content. And we previously saw that that might be a little bit detrimental to our oxidation behavior. But perhaps the higher aluminum and chromium content will offset this lower tungsten content. So this we've called DEMREF 9, and it has the nice gamma-gamma prime morphology, again with a small amount of the aluminum-rich beta phase. And we're seeing a continuous layer of alpha alumina with very thin amounts of undesirable oxide. So these two endpoints, DEMREF 8 and DEMREF 9, kind of represent a design space that we can work with it to engineer a new cobalt-based gamma-gamma prime alloy in this composition space. And what we've seen from these two endpoints is that DEMREF 9 appears to have that nice gamma-gamma prime morphology and has a very thin layer of oxide overlying the alpha alumina. But we're still getting a small amount of the beta phase, and our goal was to create a 2-phase gamma-gamma prime alloy. So for our next iteration, we'll be looking at a composition called DEMREF 10, where we'll slightly lower aluminum and slightly raise the nickel to expand that 2-phase field and move into the gamma-gamma prime region. So this brings us to DEMREF 10, which has, again, that nice gamma-gamma prime 2-phase field. We see that we're having a high phase fraction of the gamma prime. They're very nice, sharp precipitates. Our gamma prime solvus is high, about 1200 degrees C. And we're getting a thin layer of alpha alumina with small amounts of spinels on top. And another benefit to this alloy is because it has a low tungsten content, it also has a fairly low density, comparable to the 2nd generation nickel-based superalloys, which is a nice property to have if you'd like to put it in an airplane. Now, to put this into perspective, I'd like to compare what we've seen with the community. So we started out with the 2nd generation nickel-based superalloy, CMSX4, and this is the sort of behavior that we'd like to reproduce in the cobalt-based system. A high gamma prime solvus and nice oxidation behavior where you're forming a thin layer of alumina. In the ternary cobalt-based system, we don't have either of these properties. We have a low gamma prime solvus and very thick amounts of oxide scale. Other authors up to this point have been able to demonstrate one or the other of these properties. Our collaborator Akane Suzuki engineered this alloy cobalt nickel E, which has a very high gamma prime solvus, but is still not very good in terms of its oxidation behavior. It has these non-protective internal alumina particles. Conversely, Ye et al. In 2016 engineered this alloy with a nice alumina forming behavior, but it has a very low gamma prime solvus. Our alloy, DEMREF 10, has a high gamma prime solvus and some measure of oxidation resistance. So this is a very promising result. And I'd like to just emphasize these promising results before I move forward and look at some of the other properties of our DEMREF 10 alloy. Because while it's able to form alumina after 1 hour, an airplane is of course going to be flying longer than an hour and be exposed to cyclic oxidation, heating and cooling, heating and cooling. So we basically achieved step 1 of forming this alpha alumina. But our next question is, can this alloy still be oxidatively protective under longer times in thermal cycling? So we'll expose it to a longer oxidation exposure, 50 hours, both isothermally and cyclic oxidation. And what we observed is that while we're still forming our alpha alumina scale and it's very thin, it's falling off of our metal substrate. It just comes off of the underlying metal and then doesn't protect it anymore. So this is obviously an issue, but I will say that it's a little bit unfair to compare our DEMREF10 alloy to nickel-based superalloys under these more extreme conditions, because an actual commercial nickel-based superalloy will have many more alloying additions in it than our initial DEMREF10 composition. So we can consider adding some of these alloying additions that are fairly standard for industry alloys, such as grain boundary strengtheners like carbon and boron, and it's been shown that boron additions will promote alumina adhesion. Reactive element additions, which are also known to promote alumina adhesion, and we'll cast a new alloy from a commercial supplier, which will have low sulfur content because sulfur has been shown to decrease your adhesion of your oxide scale. And by tweaking these different parameters in a more realistic fashion, we arrive at this alloy DEMREF10+. So to see whether these alloying additions are having a positive effect, what we'll be doing is conducting cyclic oxidation and measuring the weight gain of our alloys. So for example, the nickel-based Rene N5 will be looking at how its weight changes over time as we increase the number of thermal cycles. So we see that as that oxide layer starts growing, we get an increase in our unit area of mass per unit area. But then in our DEMREF10, because that oxide is falling off, we see an initial mass gain followed by a mass loss as you lose that alumina scale, with a very quick amount of mass loss after about 16 hours. Now in comparison, our modified DEMREF10 plus composition is able to maintain that alumina scale beyond 100 hours. And I'm going to zoom out a little bit so you can see that we've maintained that alumina scale behavior until a net mass loss in our DEMREF10 plus alloy around 400 to 500 hours. And while this is a great improvement beyond our unmodified counterpart, we're still not quite achieving the same behavior as Rene N5, which is able to maintain that scale beyond 500 hours. So we'd like to ask the question of why is it our cobalt-based alloy is having these issues? And this is an optical image of our sample after failure after 500 hours. So to get a sense of what's going on, we're going to be cross-sectioning this alloy after cyclic oxidation and taking a look at the oxide morphology. And here we observe that across the majority of our sample surface, across these flat faces, we have a nice alpha alumina scale that appears to be adherent to our metal substrate. But where the real problem seems to lie is along these edges and corners, where we're getting these thick nodules of undesirable oxides. And to put this in the scale for you, these little bits of oxide here are this oxide across the majority of the faces. And we're getting these huge oxide nodules along the corners and edges. Now, I'll note that a good thing is that we seem to be reforming our alumina scale underneath these thick oxides. But you can see that it appears the oxide is fracturing off along the corners. We're getting a lot of spallation, and then our oxide reforms, spalls reforms, and we get this striated microstructure where we gain a bunch of mass and then it falls off. Now, what we might expect is the driving force for scale spallation to come from the thermal mismatch between our alloy substrate and the grown oxide. As you pull your sample out of the furnace, the metal will shrink more than the overlying oxide, and that will cause residual stress in your oxide scale. But what we observe from dilatometry is that both our DEMREF10 plus alloy and the nickel-based Rene N5 have a very similar coefficient of thermal expansion. So based on CTE alone, we wouldn't expect there to be much difference in the driving force for spallation. But let's actually go in and measure our stress state. Fortunately, our PSLS technique that we used before can also be used to analyze the residual stress in our alumina scale, because this characteristic alpha alumina doublet is stress sensitive and will shift over depending on how much stress is in the oxide. So what we'll do is we'll oxidize both our Rene N5 and our DEMREF10 plus, and we'll create these PSLS maps across the oxidized surface. So every pixel inside of this map is a different doublet by PSLS, and we compare how far it shifted over to an unstressed standard. And then we've colored them based on what the corresponding residual stress is. And we observe that in both our nickel-based alloy and our cobalt-based DMF10+, we have very similar residual stresses of about 4.5 gigapascals after one cycle of oxidation, after 1 hour. But as time goes on, we see that from 1 hour down to 300 hours, the stress state in Renan 5 seems fairly consistent, but in DMF10+, we get a gradual rise in our stress state that is significant beyond that of Renan 5. And you can see that we start getting fracturing of our oxide and the formation of those thick nubs along the edges, whereas Renan 5 seems very nice and adherent along the edges. So this is a very interesting result, and of course we'd like to ask, why is this behavior occurring? Why are we getting an increased stress in our cobalt-based alloys, despite the fact that the CTEs between cobalt and nickel appear to be very similar? One hypothesis is that there might be something going on inside of the alumina scale that we're growing. So here we're going to take a look at our alpha alumina scale of our grown thermal oxides after 500 hours of cyclic oxidation. So this is in the SEM. We're going to take a TEM lamella to get a closer look, and I'm going to be zooming in on this alumina down here. So we have our overlying spinels, we have some tantalate particles, but we're going to be looking at our alpha alumina scale of interest where we see that compressive stress. So I'm going to be zooming in on this layer, and I'm going to be switching to bright field mode so we can get a look at the oxide grain boundaries. So one hypothesis is that there might be increasing stress in this alumina layer if there's counter diffusion of outward metal cations and inward oxygen anions along the grain boundaries that forms additional oxide inside of this TGO layer that then creates compressive stress. So what we might like to do is to do an EDS line scan to look at how different elements partition to these grain boundaries. So what we observe in EDS is that we are getting tantalum and hafnium concentrations along the grain boundaries. And this is interesting because perhaps there is a different behavior in our nickel-based Renan 5 that will cause us to create less oxide inside of these preformed alumina layers. Now, unfortunately, in science, there are always more questions, but a graduate student only has a limited amount of time. So this is about where I ended up. But I do hope to have shown that we've established this fundamental understanding of our material system. So if there's an enterprising young graduate student out there who'd like to put these in the TEM, there is a lot of low-hanging fruit there.
We'll take a show of hands right now.
So today I have shown that we can use PSLS as a rapid screening technique to identify samples that form continuous alpha alumina scale and thinner amounts of undesirable oxides on top. We've also seen that we can use combinatorial synthesis to create a large amount of different alloy compositions at once, and combined with our PSLS, identify what the effects of different changes in elements have on our oxidation behavior. We can then apply that with a thermodynamic database to outline our design space for new cobalt-based alloy. And indeed, we've created a new alloy, DMF10, that has a combination of both desirable oxidation behavior and high gamma prime solvents. And not only that, but because we've seen there are some issues with cyclic oxidation, we have established all of this fundamental knowledge of the material system. So because we've gone through the trouble of a systematic approach, it should be easier to refine intelligently this composition to further improve its properties. And overall, I hope I've demonstrated that this is a more intelligent approach for accelerated design and characterization by combining these modern computational tools with high throughput experimental techniques. So I'd like to finish by acknowledging all of the many people who have helped me throughout the way, and of course my committee, all of our industry collaborators at GE Global Research and CompuTherm, all of the UCSB staff, without whom I don't think I would get anything done, all of the students and postdocs in Levy Group and Pollock Group, past and present, and my summer interns. A special shout out to Wes Jackson, who spent hours and hours chatting with me about oxidation, and the other Cobalt people in Pollock Group, Mike Titus, Rob Ryan, and I think Sean Murray is the last one left. And last but not least, all of our friends and family who have helped show up the way. So with that, I will thank you, and I'll take any questions.